Hello and thanks for listening. Welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help support us on Patreon if you can. There is a link in the description. We now have Academy-themed merchandise available on Spreadshirt. There is a link for this also. It is our goal to give you a good foundation in the principles of space science, and help you develop a working level of knowledge. That is why we sometimes say we want to be the trade school to the stars. Trade schools are especially important. Not everyone wants to spend 22 years in school. Some of the most important lessons we will ever learn will be self-taught. Having a good source of knowledge to get you started is extremely important. There are several levels of knowledge. Someone can be familiar with the subject, but not know the details. Or they can be knowledgeable of a subject, and have a fairly good understanding of the principles and components involved. When we master a subject, we know most of what is known about that subject, and can use that mastery to build new systems from known components. When we become expert in a subject, we know almost everything about it, and can figure out ways to make new concepts a reality. We have all become familiar with self-driving cars. We could even use one with a little instruction. But few of us could build the hardware, or write the code, that would get us somewhere alive. A mechanical engineer is knowledgeable about machines. They may have never worked on a washing machine, but they could figure it out. A master rocket engineer knows all the existing parts and systems needed to make most rockets work. Give them a warehouse and a budget, and they'll put a rocket together for you. An expert in rocket science knows all of the equations necessary to design and build a totally new system. Since we all have limited time, we must narrow our focus at every step. We want you to have a broad understanding of the foundations and principles of space science. Then you can choose whether you stay a big picture person or become a specialist in one system. Systems analysis requires us to see and evaluate the functional division of a rocket. Everyone seemed to enjoy the breakdown we did of the Merlin rocket engine in flowchart form. I cannot find where anyone has created the same for Starship. So let's do it ourselves. This is the Starship system. It is composed of a two-stage rocket, the Super Heavy booster first stage and the Starship second stage. Here you see a diagram showing the functional components of both stages. This section is for the Starship second stage, and this section is for the Super Heavy booster. As we analyze and label these functional groups, we'll review the physical structures. The Super Heavy booster and the Starship are made of stainless steel. If you want to know what kind of steel, watch this lesson. Large steel rings are stacked and welded to build the Starship. We can watch this animation by Deep Space Courier, which shows how this is done. Here we see the support structures being added, and the equipment that will be needed in the engine bay. Here we see the aft dome. The thrust puck will be attached to this. The thrust puck allows propellant to flow to the engines and transfers the force of the engines to the structure. The landing legs are attached for the Starship. Once the oxygen tank is completed, we see the common dome separating the oxygen below from the fuel above being put in place. Here we see the fuel header tank and downcomer being installed. Now we finish building the fuel tank. Once it is done, we add a forward dome and a Tesla battery pack, like this one. These provide about 200 kilowatt hours of power to the Starship. The booster will have one also. Now we add a liquid oxygen header tank at the very top with a downcomer connecting pipe to bring the oxygen down to the thrust puck for landing. Then we finish the nose cone. Put on our hinges, install the forward and aft fins, and put in our engines. Now we finish the crew and cargo section of the ship. Right now these are just empty shells, but in the future they will have multiple levels and lots of equipment, unless they're a cargo ship, in which case they will stay empty to allow room for payload. Beautiful work by this artist. There is no way that words could convey this much data, and our Starship is almost finished. We add the heat tiles, Here's a review of the oxygen tank in blue and the fuel tank in red. With the cargo space and header tanks, now our ship is complete. We'll name it the TSA Sagan, and we are ready to fly our new Starship. It should have a mass around 120 tons empty like this. The booster is constructed in the same manner. The booster will be 70 meters tall and 9 meters in diameter. It will have a dry mass of about 180 tons. These are metric tons, so each ton is 1,000 kilograms or a megagram. Here we see a booster. Let's start at the bottom and work our way up. Here we see the engine bay, just like that of a Starship. The booster will be similar and have a lot more engines, and look something like this. The engine bay will contain the rocket engines, pressurization tanks for helium and nitrogen, and these connections for plumbing and power. The Starship is using these flip-out legs right now. On the schematic you see these 4 components. The first one is a safety block to prevent the cargo clamshell from opening by accident. This is a cargo Starship. Most likely the first operational Starships will be of this type, seen here in this video. Watch the sequence of component activation. Over here on the booster, we see something marked GSE. This is where power and propellant come into the rocket or booster system. There will be a ground umbilical carrier plate that mates with this valve system. A raceway up the side will connect the engine bay with the control systems. Let's trace this raceway up a Starship. As you can see, there are electrical cables, hydraulic lines, and pipes to move liquids and gases. These beautiful renderings are made by Neil Pork and Seabass 3D Productions. Here on our schematic you see this section. This is the valve receiver plate. Here you see a picture of an older version from a different rocket. And here you see where Starship currently has its connector. This is where the ground service equipment or umbilical connects. A small detachable umbilical also connects the first and second stages of any rocket. Here you can see one between the Dragon capsule and trunk detaching after a flight abort test. There will be a quick disconnect, shown here on the diagram, between the booster and the Starship second stage. To attach here, there will be a ground service equipment or GSE umbilical with its own mating plate. The one for Starship is on the side here. I think they will try to use the same design for the booster. SpaceX likes to keep things as simple as possible. I covered these connecting systems more in depth in this video. Let's use this umbilical system to get our rocket ready for flight. First, we will need to fuel our Starship system. This is accomplished by the ground service equipment or GSE mentioned earlier. The GSE will connect to our booster and Starship through the umbilical system. There will be large tanks pretty far away from the rocket. This is usually called a tank farm. The tank farm will be connected by long pipes to the rocket. The umbilical is a connection that supplies everything the rocket will need for flight. Here you can see that it provides data transmission to and from the onboard computer, liquid oxygen with a fill drain valve here, liquid methane also with a fill drain valve, liquid nitrogen for the cold gas thrusters through this valve, power to keep the batteries charged until launch, and helium gas through this valve, which is used on the Falcon 9 and is being used on the Starship to pressurize the header tanks, seen here and here, but will eventually be phased out on the Starship if possible. Each of these tanks will have a level sensor to know how much fluid is in them and a pressure sensor to detect the gas pressure in the tank. The helium tanks only have pressure sensors. Helium becomes liquid at only 4 degrees Kelvin and will be stored as a pressurized gas in a composite overwrapped titanium pressure vessel, like the one recently gifted to a farmer in Washington state, when part of a Falcon 9 survived re-entry. The umbilical allows hardwired communication with the rocket to load and check programming and receive status reports. Technically, telemetry data is transmitted by radio, but all data from a rocket is usually called telemetry now. You can see these large antennas getting ready to receive telemetry from Starship once it's in the air. And here we see the fuel tank and the oxygen tank. Remember that heated fuel gas will pressurize the fuel tank, seen in this network here for the Starship, and here for the booster, and heated oxygen gas will pressurize the oxygen tank, seen here for the Starship, and here for the booster. I have been told that these tanks will have about 8 bars of pressure, higher than most pump-fed rockets, but no problem for the steel Starship. You'll also notice these components here. Here we see a totally independent system, not connected to anything else. It has a computer, a battery, a global position system, and these 2 components. This one is a detonator, and this one is a set of explosive charges. This is the automatic flight termination system. If the ship travels outside a set boundary, it will automatically destroy itself. It also has this ground command radio receiver. This allows the SpaceX team to blow up the ship if they think it is getting out of control or might endanger others. I cover flight termination systems more in depth in this video. Back to the umbilical. The connector for the umbilical can look like this. You can see there are sockets to accept a probe and form a seal to allow fluid flow and electrical connections. With the fully stacked Starship system, the second stage umbilical will be on a swinging arm so it can get out of the way. Here you see one of the shuttle systems swinging away at launch. During or just before launch, the umbilical systems will detach and the Starship and booster will go on internal power. The booster will have around 28 Raptor engines. I don't think we are sure what the final configuration will be. I've seen several different options. Let's look at this one. 8 engines in the middle. These would be the only ones to gimbal, probably controlled by one engine group control unit. Then these 4, and the last 16 outside engines, controlled in groups of 5 most likely, 1 for each quadrant. These will all have a control system similar to what you saw with the Falcon 9 in the last lesson. Each engine will have an engine control unit, like we saw with the Merlin rocket engine, that takes orders either straight from the onboard computer or through the booster control unit. The onboard computer is a triplicated computer system on the Starship. This means that 3 independent computers will evaluate the incoming data and compare their solutions prior to sending commands. And if one disagrees with the other 2, it is ignored. 2 computers can fail and the rocket will still work perfectly. The equivalent of the Starship onboard computer for the booster is the booster control unit. It will also be triplicated. The booster control unit will send commands to control the 28 engines. The Starship onboard computer will see how the ship is responding and use this data for decision making. If an engine develops a serious problem in one group, the engine group control unit would automatically shut it down and start to increase the thrust in the other engines in that group. I often calculate things at full thrust, but usually a Raptor will run at 70 to 75% full thrust. That takes us down from 2,210 kilonewtons to about 1,600 kilonewtons. This is done to protect the engines, and creates a margin to increase if something goes wrong. If this intervention fails, the booster control unit could send a command to the engine group control unit on the other side to reduce thrust from these engines. All of this would be coordinated by the onboard computer. If the rocket is going off course, a signal will be sent to the booster control system. The booster control system will send commands to the engine group control units. These will adjust the rocket engine vectoring systems on the center rocket engines to compensate, or adjust the throttle to increase power to one side and make a correction. Once the booster has done its job, it will fall away and go back to land. The onboard computer is still on the Starship. The Starship will always know where it is and how it is pointed with the help of these 3 subsystems: the GPS, IMU, and AHRS. We all know what the GPS does. This is the global positioning system. The GPS receives signals from satellites in orbit to know where the GPS unit is on the Earth. They are accurate for longitude and latitude down to about 30 centimeters or less, but not as accurate on altitude. Most civilian GPS receivers are only accurate in altitude to about 10 meters. The GPS can tell the rocket where it is in respect to the Earth, but not how it is pointed. The Starship could be upside down and the GPS would report the same location. You could have a GPS sensor on the top, bottom, and end of each wing, and the Starship is large enough that it might give you a rough indication of your ship's orientation. But you need something more accurate. Something that can detect tiny movements and give the onboard computer a warning to make a small correction, before a large correction is needed. The instrument for this is the Inertial Measuring Unit, or IMU. The inertial measuring units were invented during World War II. This is the Apollo IMU that guided the astronauts to the moon. These at first used spinning gyroscopes. A gyroscope is like a spinning top. When a gyroscope is spinning, it will resist movements away from its axis of spin. This resistance can be measured and used to calculate movement. If you have 3 gyroscopes, one of each spinning in the X, Y, and Z planes, you should be able to detect a turn or movement in any direction. These moving parts are all failure points, and spinning gyroscopes were later replaced by more accurate and dependable devices. A MEMS gyroscope, or micro-electromechanical system gyroscope, uses a vibrating structure in a microchip to detect movements. These are in cars for rollover detection and airbag systems. They are also used in robots, so it can track its movements, as well as cameras for image stabilization. Spacecraft have used these, including the Cassini spacecraft. There are also laser gyroscopes that use 2 canceling laser beams to detect position changes. These can be enhanced by running the laser light through a fiber optic bundle to amplify the movement effect. This is a fiber optic gyroscope. These are very robust and good for high-shock environments like gun positioning systems on howitzers. Now we have the GPS telling us where we are and the IMU telling us how we are moving. If we align the IMU with the main axis of the ship, we can then have the computer tell us if we start to pitch, roll, or yaw. It will also tell us if the rocket is feeling the correct amount of acceleration, giving us an independent measure of rocket engine performance. Finally, we have an altitude and heading reference system. This tracks how high we are above the Earth and where we are aiming our rocket. When we fly to the Moon or Mars, we don't aim for where these objects are. We aim for where they will be when we get there. Think of the altitude and heading reference system as giving the altitude and attitude of the rocket to the onboard computer. The AHRS works with the Inertial Measurement Unit and the Global Positioning System to tell the rocket where it is and coordinate its movements. The AHRS will also need to track the altitude using altimeters supplemented by GPS data. The onboard computer using these systems constantly checks to make sure that our rocket is pointed in the right direction. If not, the onboard computer will send signals to the Reaction Control System. The Reaction Control System, or RCS, will use cold gas thrusters using compressed nitrogen. The RCS will be told exactly how long to fire and in what direction to make a correction. Before we launch our rocket, we set the heading and program the flight route. The rocket starts flying following the programmed route. The AHRS, IMU, and GPS work together to tell the rocket when it is drifting off course or changing orientation. Tens of thousands of course adjustments will be made on a trip to Mars, so our colonists can arrive at just the right time. Thanks for listening. Please don't forget to like and subscribe, and I would especially like to thank all of those who help support us on Patreon. Stay safe. Ad Astra Pro Terra.